Now the question then becomes, how are we going to estimate our uncertainties in this derived density number, especially if we're starting with relative humidity? Well, if we knew everything exactly except for the relative humidity, then the only uncertainty result would come from our relative humidity measurements. So if I plugged in some values for pressure and temperature and relative humidity and said that the uncertainty in my relative humidity was 20%, so a fairly large uncertainty, then I can calculate the measured density based on just the nominal measured values. And then I can calculate one for a high level of a high value of the relative humidity and one for a low value of the relative humidity. And here I'll calculate it based on the relative humidity plus the uncertainty, and here the relative humidity minus the uncertainty. And finally, I'll get the overall uncertainty as the absolute value of the difference between the high one and the low one. And is that right? Actually, my uncertainty is going to be plus or minus, so if I'm going high and low, I really should divide by 2 there. So I'll calculate that value, and I'm then going to print this stuff out, and I'm using this percent function to allow me to do formatted printing. I find that the density, if I have a temperature of 23, a pressure of 101, and a relative humidity of 50 plus or minus 20, is 1.1818 kilograms per cubic meter. And the uncertainty range goes from 1.1793 to 1.1843, or taking half of that span between the two as a plus or minus uncertainty, 0.0025 due to relative humidity. So it's not making a huge difference in my density value. They're pretty close. Now, I could try that with some other levels of uncertainty. If I went up to, say, an uncertainty level of 40%, so I'm really uncertain. I just know whether it's humid or not so humid. I see things increase and my uncertainty level more or less doubles in my result as well. So that makes a certain amount of sense. Let's go back down to 20 here. And let's try it at a different temperature. Let's try it at 80 degrees Celsius. I'm now seeing a considerably bigger shift in density. I've got a different density value entirely, and I've got a fairly large uncertainty due to relative humidity. That's because the range of the amount of water that I can have in my sample is considerably larger at this higher temperature. So even without changing the uncertainty in the relative humidity, I can dramatically change the uncertainty in the resulting density calculation. Now we can do the same kind of calculation to find out how much uncertainty we have from pressure and temperature, if they were the only things changing. So we'll go through and we'll do the calculation that we already did. That's this one here. And then I'll get a value for temperature as the absolute value of the difference between the temperature plus a little bit of uncertainty minus the temperature as it was specified. And I can print that out and find out what the uncertainty is due to the temperature. Then I can do the same with the pressure here. I can calculate the uncertainty in the that's due to the pressure as the density calculated with the pressure plus a little increase in pressure minus the pressure at the base conditions. I can print that out as well. Now finally, I can take all of those and put them together as a sum of the squares and then take the square root, because we know that the uncertainties combine as the sum of the squares and then we take the square root. That's the way our Gaussian distributions combine. And this accounts for the fact that what we're seeing is the random effects. Sometimes they reinforce each other and sometimes they wind up offsetting each other. Now, the worst case we could possibly get is if we just added all the uncertainties together. We've made absolute values of all of these, so we're taking them as a positive value for our plus and minus. And if we assume that they all go in a positive direction all at once in the worst possible way, that'll give us our worst case tolerance if everything went wrong all at once. So let's run that cell now. And we get out some similar results to what we got before. We've got some densities for a given set of values. So here we are at 50 degrees Celsius. We've got an uncertainty due to relative humidity that's relatively small. We've got somewhat bigger uncertainties due to our uncertainty in temperature and pressure. And our overall uncertainty, when we combine all of these in that sum of the squares, will be 0.0244 or 2.14%. So it hasn't been a result of just adding them together. We've added and summed the squares and then taken the square root. Now, if we just added them all together, our worst case value would be 0.04, almost twice what our actual expectation 95% of the time will be. So it's really important to do this combination with the sum of the squares and then take the square root to avoid over dramatizing on the absolute worst possible outcomes we could get. So if we play around with these results, we'll see once again that the overall uncertainty changes as a function of temperature, pressure, and relative humidity, even if the individual uncertainties remain the same. So let's go up here, and I'll change my relative humidity to 20%. I'm not changing the uncertainties in the quantities at all. I'm just changing the conditions I'm evaluating under. And what we see is that the overall uncertainty went down. If I change my temperature from 33 down to 25, I once again see a change in the overall uncertainty. And so we get values that change depending on what conditions we're measuring at. So we need to always be calculating our uncertainties every time for every particular set of conditions. And that can get kind of tedious. Now let's have a look for whether or not we can come up with an analytical function. Now up here, for example, for our uncertainty in the density due to pressure, we had an absolute value of the value we've got for the density at P plus a little bit minus the value we got for the density at just standard conditions. So if we go down here, we can write that like this. The uncertainty in the density due to pressure is equal to the absolute value of the density for the pressure plus the uncertainty in the pressure and the temperature and the relative humidity minus the value in the base case. Or we can multiply top and bottom by the uncertainty in the pressure and wind up with this expression here. Now, this is starting to look a lot like a derivative. This is the difference for a small change divided by the size of that small change. So if the uncertainty in the pressure was small, then this would just become the partial derivative of the density with respect to pressure. And then we wind up with the uncertainty in the density due to pressure being equal to this derivative, this sensitivity of the density to the pressure, times the uncertainty in the pressure. The overall uncertainty can be obtained by getting the sum of the squares for all three. So we'll have di rho di p up all squared plus di rho di t ut all squared plus di rho di relative humidity, uncertainty in the relative humidity, all squared, and then we'll take the square root of it. And that'll give me my uncertainty in the density as a function of these derivatives. And I don't need to keep those absolute value signs because when we square, all of these quantities are positive anyway. And we can generalize that result for any derived result of calculation from a bunch of different measurements. So we're measuring x1, x2, x3 up to however many x's there are. And we can find that the uncertainty in the result is equal to the square root of the sum of the squares of all of the individual contributions to the uncertainty. So dir dx1 ux1, dir dx2 ux2, both all squared. Sum all of that up and take the square root, and you can get an analytical value for the expected uncertainty. And you can find this in many textbooks, including Figliola and Beasley. And using this result works really well if all you've got is a pencil and paper. However, it depends on several things if it's going to be effective. We're assuming that the function r is linear, or at least can be approximated as being linear in the range that we're interested in for small amounts of uncertainty. We're also assuming that the uncertainties really are small. So if they get big, that may introduce a little inaccuracy. This is the really big one. The function r is assumed to be easily differentiable, that you can calculate these derivatives easily with the skills that you've got. And that can be a problem if the relationship is at all complicated, like the one above with the relative humidity in it. I would have a hard time differentiating that. I'm sure you would too. So in application of this equation, it's often also incorrectly assumed that if we just do a single uncertainty calculation, that will cover the whole range of results, and it won't. So it's often better, because we've got computers and we're processing all of our results with computers anyway, often better to follow this numerical approach that we used above to develop an uncertainty directly for every quantity that we calculate. And that can be considerably advantageous. And it doesn't require that we remember how to take derivatives of complicated functions. So one of the things we can do is we can build that uncertainty calculation right into the original function. So you'll remember I had this rho ideal RH function that calculated a measured value of density based on the values that we had for pressure and temperature and relative humidity. I've still got that function sitting up there. So now I can build a new function that also calculates the uncertainty at the same time, right on top of it. And I can pass the result back. I can pass back both the results for the actual value and the uncertainty in that value when I come back. Now, I could also send values over with both the measured value of the pressure and the uncertainty I have in the value of that pressure. And then when I went to calculate the measured density, I could take the first value. And when I went to calculate the uncertainty, I could take the second value that I had passed to the function with this tuple. A tuple in Python is two things that are grouped together like A and B that you can pass around, sort of like an array. And they can also be different types of data. So when I pass a tuple of pressure values, one of which is the actual pressure and the other is the uncertainty in that pressure, then I can use it in the function here to get a result. So calculate the resulting density based on the first value in each of pressure, temperature, and relative humidity. Calculate the uncertainty for the density based on the value of density I get for the pressure value plus the uncertainty of pressure and the temperature and the relative humidity, minus the ideal value that I get with just the pressure, the temperature, and the relative humidity without the uncertainty added in. So that first term here is the uncertainty due to the pressure, and I'm going to square it over here. The next one, I'll add the uncertainty due to the temperature. So I've got temperature plus the uncertainty in temperature here, and I'm going to square that. Then I'll calculate the uncertainty due to the uncertainty in the relative humidity and add the square of that as well. So here I've got relative humidity plus the uncertainty in the relative humidity, and I'll square that and add it on. Now, if I take the square root of that sum, that should give me the uncertainty in the density. I can pass back the calculated uncertainty and pass back the calculated density here and the calculated uncertainty in that density. And one of the pluses is I can define this function without knowing anything about the characteristics of the underlying function, that rho ideal RH, other than I have to assume that it's reasonably well behaved, that it's reasonably linear, and that it doesn't oscillate up and down or have discontinuities right near the range where I'm measuring. So it would have to be a really badly behaved function for it not to work, not just one that I have a hard time calculating derivatives of. So now, if I take the temperature as 23 with an uncertainty of 1, and the pressure as 101 kilopascals with an uncertainty of 2 kilopascals, and the relative humidity as 50% with an uncertainty of 20%, I can calculate the resulting tuple of density and its uncertainty value by calling this rho ideal RH function. Now let's see what comes out. Whoops, I get a name error. What happened here? Oh, I guess I didn't run this part of the code. Now I don't get a name error. I had to actually define this function and run the code to get it to show up. So I get the density that I expected, I get the uncertainty that I expected, and if I change the values, I'll get a change in uncertainty about the same way that I would expect. So now we can go back to the beginning. We can do the same kind of plot we started out with, but now we can include an uncertainty band for our results. So let's have a look here. 100 points to plot. I've got uncertainties associated with temperature, pressure, and relative humidity because I know something about these measurements. I'm going to go over a pressure range and a temperature range. I'll get my relative humidity and my density, and I'll have an uncertainty function as well. And then for I going from 0 up to 100, my number of points that I'm going to plot, I'll get the density and the uncertainty as the returns from this rho ideal RH sub u function, the one that I just defined up here to calculate the uncertainty at the same time that I calculate the density. And I have to feed it values of pressure and uncertainty of pressure, temperature, uncertainty of temperature, relative humidity, and uncertainty in relative humidity as tuples in order to do that calculation. Finally, I can plot out the individual lines, and that's the green and the blue lines, the red and the orange lines that I expected. But now I can also plot some fill in between the actual density minus its uncertainty and plus its uncertainty with a little bit of transparency so that I can put a shaded bar on here to represent what my uncertainty is. When I run this one, I find that these ones, the green and the blue, 20 degrees C, both are at 20 degrees C, have considerably lower uncertainty in my density calculation than these ones at 70 degrees Celsius, which have considerably higher uncertainty in the density calculation. And that uncertainty is coming in because of the magnitude of the relative humidity contribution at those different temperatures. 70 degrees Celsius air can hold a lot of water, and the uncertainty in that relative humidity will dramatically change the uncertainty in our estimated density. So if I reduce the uncertainty in the relative humidity, let's take it down to 5. Then that uncertainty in the relative humidity isn't making a big contribution anymore, and these uncertainty bands become about the same. So if I go back up to say 25, fairly large error in the relative humidity, I'm back to the situation here where I've got large bands of uncertainty at the higher temperatures. So this is an approach you can take to finding out the uncertainty for derived quantities. By all means, if you've got to sit down at an exam and you like to do calculus, do your calculations for combined uncertainty this way with the derivatives. And it's important to understand what's going on here. But more practically, think about it in terms of the calculation that we did up here, where we're collecting the effects of each of the different quantities on the overall uncertainty, and then down here, taking the sum of the squares and taking the square root of it. If you want to get really fancy, I'd like to encourage you to always be keeping that uncertainty in mind and derive a function like this one, where you calculate the uncertainty right alongside calculating the actual value, so that you're always carrying around an uncertainty estimate in addition to what you think the measured value is. So we'll explore how to use this in some of our assignments during this segment.